everyone, and welcome back to another exciting day. We have Physics Lab 3, Black Hole and Orbits. Let's get it. First, we got our purpose and description. So we wanted to create a computational model that finds the mass of the black hole. In part 1 and part 2, we used kind of that calculated mass to determine the initial velocity and have it moving around the planet without crashing. We created 2 computational models to simulate gravitational motion and modified them to fulfill our different purposes said above, and these exemplify the effects of Newton's second law and how it affects momentum. So that leads us into fundamental physics principles and variables. So we got Newton's second law, force equals mass times acceleration. We got the net force is the change in momentum over change in time, and you can manipulate that in other ways. And it's very important to know that F net equals F parallel plus F perp. And we got gravitational force, attraction between two massive bodies. We have F grav equals GMM over R squared times R hat for direction, and we got position and velocity update like the other 2 labs. So now we got coding part 1. This is the experiment. We got a visual output. We have system and surroundings, the star, and then the black hole in space was the surroundings. And then these are the initial conditions. We were given the gravitational constant, mass of the star, and change in time. And these are kind of the computations of it. We looked at the velocity, initial and final velocities, P initial, P final. We calculated the change in velocity and change in momentum, which is needed for Newton's second law. In the momentum principle, we needed the parallel force, the perpendicular force, and then we know the mass, and then this was the finding the mass of the black hole using F net, and the magnitude of the star's position squared, and this is the gravitational equation. We got the mass to be this number. And this was the part 2. We got experiment. This is what it looked like for mine. System was the star, surroundings black hole in space. Initial conditions was this right here. The time we had to modify to make faster, so we multiply by 7. And then we manipulated the speeds for this to make sure they didn't crash. This more computations to find the different gravitational forces of like ship to moon, planet to ship, and then this would make sure that we didn't crash into the moon. Results, we got initial velocity as this. And then discussion, so we did assume, we kind of created a simulation, so it won't always represent how reality is, and we assumed that there were no outside forces acting on the system. Accuracy-wise, we used trial and error to find velocities, and a perfect answer doesn't exist, so we can't really say that it was the most accurate. And what does it mean? So how is the net force and its parallel perpendicular components different from the rate of the change in momentum in its components? Well, we know that F net equals the change in momentum over the change in time, right? So mathematically, yes, they are the same. But in reality, one is easier to measure. So for net force, we have to know like each factor of exerting a force on the system. And for rate of change in momentum, all we need is the system's change in velocity, mass, and time. So what if we wanted to predict the motion of the entire system? What would you need to know, or what would you need to include in your computational model? Well, you would have to think about all the interactions in the system, like would there be any dominant interactions, or would they all contribute more or less equally? And I kind of decided that like the computational model would have to include the calculations for the gravitational force of each object in the system on all other objects on the system. And the mass of the black hole is the largest, so the gravitational interactions, including this black hole, would be dominant. So when we're thinking about kind of the purpose of this lab, we want to think about how we use F net equals mass times acceleration, but to a different level. So in this experiment, we really focused on how perpendicular and parallel forces work together in centripetal motion, and using that centripetal motion along with gravity, the GMM over R squared times R hat. Which was extremely important, and we know that there's going to be a force perpendicular to the object in centripetal motion that will always be pointing towards the center, and this happens in orbits all the time. So it's a very applicable lab, I'd say. And yeah, I hope you had a great time listening to my lab, and have a great Friday night, and thank you. Yeah, bye.